Welcome to the lecture on heat flow in welding. So, in the last lecture we discussed about the different heat sources which is used in welding, and typically we also got the idea about the efficiency of those heat sources. Now, we will try to understand how there will be heat flow in the welding. So, we will try to have the understanding about the fundamentals of the heat flow equations, and then also in our coming lectures we will try to have an understanding of the temperature distribution in the welding. So, in this lecture we will try to have the understanding about the basic equations which govern this, which talk about the heat flow in the welding. So, heat flow in welding basically is due to the heat input by welding source in limited zone, and further its flow into body of workpiece by conduction. So, certainly we know that we are using a heat source. That heat source will generate the heat, and that heat will be basically locally in a local manner. It will be doing its job by melting, but then the heat which is there, that will be basically flowing into the body, because all around that zone where the metal is melted you have the metallic material. So, that takes the heat from it. So, that goes by conduction. And certainly when you have a liquid metal pool and which is exposed to the surrounding, which is exposed to environment, so there will be some loss to the surroundings by radiation, and there will also be some loss or heat flow by convection also. So, but then we neglect, because that is a very small amount as compared to the heat which is flowing into the body using the conduction mechanism. Now, what we see in case of welding process is that you have a source which is the heat source, that is where the arc is striking the the metal. So, in that zone, so that basically there basically large amount of heat is generated, and also that is moving along certain direction. So, basically if you try to see, then you can have, consider this welding process can be considered typically a problem of heat conduction with a moving heat source, because the source which is there, it is basically moving in certain direction. Now, certainly that you must have the concept about the heat flow, what are the governing equations for heat flow, and then only you will be able to have the idea about what will be the temperature at certain point. So, you will have some assumptions also, and there will be further simplification using the assumption of workpiece with larger dimension. So, if you take the workpiece of larger dimension, in that case the infinity concept is coming into picture, and that tells that the temperature at farthest end of the workpiece in all directions remain unchanged. So, wherever we are typically thinking about the heat transfer at that particular point, and if you take the point which is quite distant from there, so there the temperature in all directions basically remain unchanged. So, you will have a temperature distribution pattern can be seen, and that can be so that will be another simplifying assumption. So, that basically leads to the quasi-stationary state we call it as, and this quasi-stationary state means that a condition in which the observer at a point will see a fixed temperature field all around the arc at all times. So, if you have an observer and he looks at the temperature field, so what he will see that around the arc a field which is generated. So, you will have a fixed temperature field. So, if you have an arc all around, you will have the constant temperature field. So, it will be something like you have you have a direction in which you are welding, and what you see is that if you are having you are at this point at this moment. So what you see is that your the temperature distribution will be moving like this. So this will be your this way your temperature distribution will move like. So this is temperature field in that can be considered to be in the case of quasi-stationary state of welding, and you will have the temperatures so you will have, suppose this is the temperature T1, this is temperature T2, this is temperature T3, this is temperature T4. So and then if you are moving in certain direction, so after some time at present time, suppose this was in the past, so at present you will have again you are having this point. So this way your temperature field will be looking like. So again you will have the temperature lines like this is T1, this is T2, this is T3 and this is T4. So this is your direction of welding, and in fact the T1 is smallest and T4 is the largest one. So T4 is more than T3, then T2 and then T1. So that way your so that's talking about. So this way your heat flow will be taking place. Now what happens that in the case of so we are talking about this so what we see is a fixed temperature field all around the arc at all times. So that is what we are seeing, that you have, if you look at it, the observer will see all around the arc he will be seeing this fixed temperature line. Now if we try to determine the temperature at any point in the workpiece during welding, so certainly the problem can be solved considering basic Fourier's equation. So equation of heat conduction is there in Fourier's heat conduction equation, and as we know that you will have what we see that in the case of Fourier's conduction equation, if you try to revise, so it tells that the rate of heat transfer. So if you go to the Fourier's equation, Fourier's law of conduction, so it tells that the rate of heat transfer, so that is per unit time. If you look at this unit, that is if you call it as a Q, so Q will be a product of so Q basically will be a product of area A. So it will be area A, and then you will have the temperature gradient, so dou T by dou X. So that is your temperature gradient at the section, and then you have the thermal conductivity. So that is your the Q defined as, and we P2M sign negative, because heat flow will be occurring in the direction of decreasing temperature. So that is why we call it keep this signal sign as negative, and this is also known as the dq by dt. So that is rate of heat flow. So we call it as the dq by dt. So dq by dt can be taken as this so that is your Fourier's law of heat conduction, and it can be derived by if you go for the one dimensional case, then you can have a geometry where you must have done earlier. So if you take a geometry of this type where there is unidirectional heat conduction, so you will have such a slab through which the heat is moving from this side to this side. So you will have this dimension as dx, and then in this case you will have the heat transfer. So if you look at the temperature, this will be at higher temperature and this will be at lower temperature. So this this difference, that will be dt. So, and then you will have other dimensions like this is taken as dy, and you have so this if you look at the value, if this is taken as dqx, so so this distance will be x plus dx, and this is taken as dqx plus dx. So, so that way you can have so we can get the expression for that. You can have the you know some names to the faces, and accordingly you can get the expression. So, this is the condition of unidirectional heat flow, and in this there are many assumptions like heat flow in the y and z direction. So, here you are having the assumption that you know you are taking these in the heat flow in y and z direction is 0. And accordingly, so you solve this equation and try to have the temperature field. Now, if you take the 3 dimensional heat flow, so if you go to the 3 dimensional heat flow equation, so in that basically we are talking about the simple cube, and if you take a cube of of this shape, so that is how the cubic shape can be taken, and in this you can have this this as A, B, C, D, and similarly you have E, F, G, H. So you will have E, F, G, and H. Now, in this case the heat transfer will be, heat flow will be in all the 3 directions, x, y, and z. So you will have dqx here, and this from this side it will go dqx plus dx. Similarly, you will have so this is your y. So this is your x direction, this is your y direction, and this is your z direction. So in this case you will have here dqy, and then from here it will move. So that way it will go dqy plus dy. Similarly, you will have dqz and dqz plus dz. So that way you will have the flow of heat from all the faces in the case of 3 dimensional geometries. Now, in this case as the geometry indicates, you will have the volume of the geometry. So volume can be taken as dx, dy, and dz. So this will be the volume of this cubical element. Now, dqx is the quantity of heat which is entering towards the x face. So this is your direction x, and this is direction, this this dimension is dx. Similarly, this dimension will be dy, and this dimension will be dz. So that's how so we take it as dx, dy, and dz. Now you can have the you can use that Fourier's law of conduction, and you can get the expression for dqx by dt. So dqx by dt will be minus of k a. So a will be the area of this face. So that will be this is your this side and this side. So this side is dy and this side is dz. So it will be dy dz. And then you will have the term that is temperature gradient. So that will be dou T by dou x. So that is your the use of the partial differential term, and if you take the dq x plus dx. So if you find the dqx plus dx term, now dqx plus dx term can be written using the Taylor expansion theorem. You can write it as dqx, then you will have dou by dou x of dqx then into dx. Similarly, the other terms will be going out ahead of this. So if you take dqx plus dx minus dx, so dqx, so dqx plus dx minus dqx, it will be dou by dou x of dqx dx. So, that will be your this. So, but if you get the value of dqx minus dqx plus dx, so it will be minus of dou by dou x of dqx into dx. So, that way you get this term dqx minus dqx plus dx, it will be minus of dou by dou x dqx dx. Now, if you substitute this value of dqx and if you so in this value you have the if you find this dqx value. So, if you substituting this value, your this value becomes minus of dou by dou x, and then you take minus k and then dy by dy into dz, and then you have dou t by dou x. So, that is what you are taking the value of dqx, and then you will have the dx into dt. So, that is your this dt will go into this side. So, that way you are getting this term, and what this way you are coming to what you see is that this dx, dy and dz will come from this side. So, you will have so you have minus sign here and minus sign here also. So, that way it will be a positive sign. So, you will have dou by dou x of k dx, dy, dz. So, you will have and dx, dy, dz can be taken out. So, you will have so that will be dv. So, it will be k and dou t by dou x, and your dx, dy, dz, because it is a constant value, so it can go out. So, you will have the term dv and dt. So, that way you are getting the value of the dqx minus dqx plus dx. Similarly, you can have the value for the dqy minus dqy plus dy. So, that is heat is flowing from here to and the difference of rate of heat flow, that way you can find. And similarly, dqy minus dqy plus dy, that will be according to this this equation. You can have dou by dou y of k dou t by dou y dv dt. So, that way you may have the dqz minus dqz plus dz. So, in a nutshell, what we get is dqx minus dqx plus dx. It will be dou by dou x of k dou t by dou x and then dv dt. Similarly, dqy minus dqy plus dy, it will be dou by dou y of k dou t by dou y dv dt, and dqz minus dqz plus dz, that will be dou by dou z of k dou t by dou z dv dt. So, that way you are getting the three expressions. So, if you talk about the total heat gained, so if you talk about total heat gained in this cubic element, total heat gained in cubic element, that will be dq x minus dqx plus dx plus dqy minus dqy plus dy plus dqz minus dqz plus dz. So, in cubic element, if you talk about the total heat gained, it will be dq, and it will be the summation of all these. And if you write this, it will be, so you can take the dv term out, and you have the dou by dou x of k dou t by dou x plus dou by dou y of k dou t by dou y, and plus dou by dou z of k dou t by dou z, and then you have the term dt coming into picture. So, So, that way what you see, this dq term is coming as the dV into this. Now, further if you talk about the heat gained in the system, it is nothing but it will be expressed in terms of increase in the internal energy of the system. So, if you talk about the internal energy increase of the system, so that is your dE, it will be so we know that that will be mass into the specific heat into temperature difference. So, it will be mST, and you know, so you have mass as volume into density. So, density is rho and volume, we know that volume is dV. So, that is your dV is the volume of the that element. Then you have specific heat, that is and then you have temperature difference. So, that is dT and dot dt. So, that way you will have this expression, and basically both can be equated. So, if you try to equate now in this equation, you know that all the things, this is the Cp specific heat at constant pressure, and you have other terms known to you. So, what you do is you have to equate these two values. So, you will have dq same as dE. So, if you do that, you will be getting the expressions, and that will come as, so you will have dV into dou by dou x of k dou t by dou x plus dou by dou y of k dou t by dou y plus dou by dou z of k dou t by dou z, and if you take this dt term, that will be same as rho dV and then Cp dt by dt into dt. So, so that way you will have this term, and if you you know if you take the k as uniform in all the directions, if the k becomes constant, then this k will come out, and this dV will be also be cancelling, the k will be coming out. So, your equation will come as k into dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square. Now, this will be dV term will be cancelling. So, you will have the rho and Cp, and then you will have dt by you know dt, and this dt term will also get cancelled. So, that way you know this. So, if you keep dt here, it will become also coming as dt, and anyway that dt has to go. Now, if you talk about that condition in which with respect to time, basically there is no temperature difference. So, from here you are getting the expression, that is you can have these equations written like dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square. That can be taken as rho Cp by k and dt by dt. Now, this is basically the equation of the three dimensional you know heat conduction in solids. Now, what happens that we try to define this term rho Cp by k. So, k by rho Cp is taken as the term alpha. So, if you take alpha as k by rho Cp, so in that case your equation can be written as you know, so Fourier equation becomes dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square. That is written as 1 by alpha into dt by dt. So, this is known as the Fourier's you know law, Fourier's equation of the three dimensional heat flow. Now, this equation is basically implied in the case of welding, and then the temperature distribution basically is tried to be you know found out. So, in the case of welding, as we discussed, that you have what we see in those cases, that if you take a very large plate where we had seen that we are using this infinity concept. So, now in this case, suppose you have you define. So, so what you see is that this is your x direction, and this is your certainly z direction. So, what you see, and this is your x is your direction of welding. Now, in this case, what happens that your source which is there, the heat source which is there, it is not fixed at any particular point. Basically, it is moving. So, and moving in this x direction. So, and so the arc which is here at this point, it will be moving to this point at some point of time. So, if you take if you want to find the temperature distribution at any point, that is if suppose you are taking this point as A, and if you want to find the temperature distribution at this point x, y, z. Now, in this case your tip of the electrode will be moving in the x direction. So, other distances will remain fixed except the x coordinate system. So, what we do normally in such cases, we are basically changing this coordinate system. You have to take you have to shift the coordinate system. So, along the x direction, basically you will have the another parameter which will be coming in place of x, and what we do is in that coordinate system we are taking this because if suppose v is the velocity of welding, in that case we are basically taking zeta, and zeta is taken as x minus vt. So, at any time taken by welding, at any time if you try to find, so you will have y and z coordinates remaining fixed, but the x coordinate, because this if you talk about the distance of this point A, so that will be changing. So, because of that change, we are changing this coordinate system with respect to the tip of the electrode, and zeta we are taking as x minus vt, where the v is the welding speed and t is the time taken by welding. So, that is starting from origin O. So, if you take this origin as O, so after time t it has to travel, it will travel a distance of suppose vt. So, this distance which is x, it will be x minus vt. So, that way your zeta will come into picture. So, apart from, so instead of the coordinate as x, y, z, it will be zeta y, z, that will be taken, because there is movement in certain direction, and that will lead to certain changes, because if zeta is taken as x minus vt. So, your d zeta by, if you take d dou z by dou zeta by dou x. So, dou zeta by dou x will be coming as 1, and if you take the dou zeta by dou t, so that will be certainly, as you see, it will be taken as minus v. So, so t will be the function of basically zeta and time. So, because the t is the function of zeta and time. So, what we get further, t, since it is a function of zeta and time. So, we have to have the expression for dou t by, so the differentiation of the dt with t. So, if you take the differentiation of dt by dt, so it will be taking, so we will have the partial differentiation principle. So, once you will differentiate in terms of zeta, and then d zeta by dt, and then plus further partially differentiate with respect to t, and then we will have the dt by dt. So, that way you will have the differentiation dt by dt, and as we know dt by d zeta. So, dou t by dou zeta will be as usual, and d zeta by dt, that we know that it is coming as minus v, and then dou t by dou t is anyway there, and dt by dt is any, so it is 1 itself. So, it comes as minus of v and dou t by dou zeta and plus dou t by dou t. So, that way you are getting the expression for dt by d small t with respect to time. Similarly, we can have the expression for dou t by dou x also. So, you will have the expression for dou t by dou x, and dou t by dou x will be dou t by dou zeta into dou zeta by dou x d zeta by dx. So, it will be dou t by dou zeta and d zeta by dx. So, and that will be dou t by dou zeta, and then it will be d zeta by dx. We have already seen that that is 1 itself. So, it is so dou t by dou x is dou t by dou zeta. So, we are getting dou t by dou x is dou t by dou zeta. Similarly, if you so further we can differentiate these expressions and try to have the expressions for the dou square t by dou zeta square. So, if you further differentiate, say you are differentiating with respect to if you are differentiating further with respect to x, this equation. So, it will be dou square t by dou x square. So, it will be dou by dou x of dou t by dou zeta. So, that will be basically dou by dou zeta. So, you can write as dou by dou zeta of dou t by dou zeta, and then dou zeta by dou x. So, this will be d zeta by dx. So, you can write it as dou square t by dou zeta square. So, what you see that dou square t by dou x square will be dou square t by dou zeta square, and dou t by dou x is dou t by dou zeta, and dt by dt will be minus v of dou t by dou zeta plus dou t by dou t small t. Now, these expressions will be used to find the temperature distribution in the case of welding, that we will do in our next lecture, where we try to find in actual case when you have a moving heat source, what will be the temperature distribution. So, that way we will see it in our coming lecture. Thank you very much.